Welcome to Lecture Online. Now in this video we have a more typical example of how to use Kirchhoff's rules. Matter of fact, in this type of circuit, Kirchhoff's rules is ideal, and the reason for that is we have multiple loops and we have multiple voltage sources. That's usually a good indication that you want to use, at least try Kirchhoff's rules on this type of problem. We're supposed to find the currents in each of the branches. We want to find the current through the 4 ohm resistor, through the 6 ohm resistor, and through the 8 ohm resistor. How do we do that? Well, we start out by assuming a direction in each of the branches. Since the positive end of the battery is on this side, I'm going to assume that the current flows in this direction through this branch, and I'll call this I1. Here we have the voltage source with the positive end on this direction and on this side, so I'm going to assume that the current flows in this direction through this branch, so let's call that I sub 3. And then through this branch, if the two currents come together, we can assume that the current will flow in this direction through here. Let's call that I sub 2. Now, I may be wrong. It could be that I sub 3 is actually in the opposite direction, that the voltage, the potential difference across this battery is so large that it overwhelms this one and sends current in this direction. That is possible. But it doesn't matter if we assume the wrong direction. In the end, if we assume the wrong direction for I3, the answer will come out negative, which then indicates it's actually in the opposite direction. So you don't have to sit there and worry, oh, did I get that right? Even if you get it wrong, it doesn't matter. Now we have the two laws of Kirchhoff. The first one says that the sum of all the currents entering a branch or entering a node should equal all the currents, or the sum of all the currents leaving the node. And we also know that the sum of all the voltages around in a loop should add up to 0. We're going to use two loops. Here's loop number 1. And it's always a good idea to indicate the direction that you're taking when you're going around the loop. And here, that's loop number 2. And again, indicate the direction you're going to follow when you go around loop number 2. So let's come up with the 3 equations. We need 3 equations because there's 3 unknowns, I1, I2, and I3. If I take this node right here, I notice that I1 plus I3 add up to I2. These are the two currents entering the node and one current leaving the node. So equation number 1 tells us that I1 plus I3 equals I2. The second equation can be found by going around loop number 1. I can start at this node right here, go around loop number 1, get to the same node, and add up all the voltages. So equation number 2 is obtained by going from here across the battery from negative to positive. That's a positive 10 volts. Going across the resistor in the same direction as the current means we have a voltage drop. So we get minus 4 times I1. Coming down through this branch here in the same direction of the current, that's another voltage drop, minus 8 times I2. Then I get back to the same point where I started, so therefore this should add to 0. That's equation number 2. Equation number 3 can be found by starting at any node in the loop. Let's start with this node. Going from here in a clockwise direction across this resistor against the current, that means that's a voltage rise. That's plus 8 times the current, I2. Then in this direction, that's against the current, that's the voltage rise, plus 6 times I3. And then from here to there, that's from the positive end to the negative end of the battery, that's a minus 4 volt drop. Oop, we don't have to write the units, just say 4. And since we can then get back to the same point, that adds up to 0. There's the 3 equations, and we can use those to find the 3 unknowns, I1, I2, and I3. I like to use this equation first because it usually already has one of the currents in terms of the other 2. We can take that to substitute that into this equation right here and into this equation right there. So the 2 equations, 2 and 3, will now change to the following. 2 is now going to be equal to 10 minus 4 times I1 minus 8 times, and instead of writing I2, we can write I1 plus I3. I1 plus I3. The third equation, same thing. Instead of writing I2, I can write I1 plus I3. This gives me 8 I1 plus I3 plus 6 I3 is equal to, oh, not equal yet, minus 4 is equal to 0. Simplifying the 2 equations, writing all the i's on the left side and all the constants on the right side, equation number 2 So we keep these two going. Equation number 2 now becomes minus 4i1 minus 8i1 is minus 12i1. Minus 8 times i3 is minus 8i3 equals, when we bring the 10 to the other side, becomes a minus 10. The third equation, we have 8 times i1, 8 times i3 plus 6, that's plus 14i3. And that equals, when we bring the minus 4 to the other side, it becomes a positive 4. Now notice that if I multiply the second equation by 2, and I multiply the third equation by 3, the minus 12 becomes a minus 24, the 8 becomes a plus 24. When I then add the two equations together, the I1s drop out, and I only am left with a single unknown which I can solve for. So the two equations now become as follows. I'm multiplying this equation by 2, I'm multiplying this equation by 3, and I get, this is equation number 2, equation number 3, minus 24 I1 minus 16 I3 equals minus 20, and this equation plus 24 I1 plus, that would be 42 I3 equals plus 12. When I add the two equations together, notice the I1s drop out. 42 minus 16, that would be 26 I3. Let's see, 26 plus 16, that's 42. And this becomes 20 minus 20 plus 12 minus 8. Which means that I3 is equal to minus 8 divided by 26. And let me get a calculator for that. 8 divided by 26 equals 0.308. Minus 0.308 amps. Notice that we end up with a negative current, which means my initial assumption that the current was in a counterclockwise direction in this loop, it's actually in a clockwise direction. So the negative indicates that the actual current is in the opposite direction. But that's okay, we can leave it like that. That we can then realize the current is simply in this direction. Now we need to solve for I2. Let's use this equation right here to solve for I2. 8 times I2, so I'm taking this equation over here, 8 times I2 plus 6 times I3, which is a negative 0.308, minus 4 equals 0, which means that 8I2 is equal to a positive 4 plus 6 times 0.308. And then, of course, we divide both sides by 8, which means that I2 is equal to, so multiply times 6 plus 4 and divide by 8. And I get 0.731. 0.731 amps, which is the current in I2. So I2, I do have the correct direction because I got a positive answer. Finally, we can solve for I1. Using this equation, I can now say that I1 is equal to I2 minus I3. So I2 is equal to 0.731 amps minus a minus 0.308 amps. That makes that a positive. This is therefore equal to 1.039 amps. And there's I1. So it gives me the three currents, I1, I2, and I3. The way I've drawn it, we now realize it's in the opposite direction. And that's how we use Kirchhoff's laws to solve a multi-loop, multi-voltage source problem like this.